Hello everyone, myself Devashish Das, Assistant Professor of Electronics Communication Engineering Department of Greater Kolkata College of Engineering and Management. In this video, we are going to study about the different topics of analog electronics and its applications, how the analog electronics apply in our different fields of electronics. In this video we are going to study about it, different circuits and its part we are explaining one by one in this topic. Analog Electronics 1. This course is mainly for diploma students of electronics and telecommunication engineering of third semester. The paper code is ETCE AE1S3. Hello, welcome to another session of my video lecture. In this session, we are going to cover up following topics. First, we cover up the common emitter configuration. Then we cover the relationship between the alpha and beta, the gain of the transistors, different types of gain. Then we cover up the collector current expression. Then we discuss about the common emitter characteristics, then the common collector configuration, then we discuss the common collector characteristics. So we're going to discuss this topic one by one. So let us begin. First comes the common emitter configuration. In case of the common emitter, terminology is derived from the fact that the emitter is common to both the input and the output side of the configuration. In this figure you can see two type of transistor is used. One is NPN transistor, another is PNP transistor. In case of the NPN transistor, the signal is applied to the base, and also for the PNP transistor the signal is applied to the base. So base is the input terminal of the transistor. To get a proper transistor action, the emitter base junction should be in forward bias and the collector base junction should be in reverse bias. So this type of biasing has to be provided. So it is a p-type, so it is a NPN transistor, base is p-type region, so our emitter base junction is forward bias. So the positive terminal of the battery is connected to the base and the negative terminal of this battery is connected to the emitter of the transistor, and in this case the emitter is common. And in case of the collector junction is reverse bias, so a positive terminal of the battery is connected to the inside of the collector region, and in this way the collector makes a reverse bias potential with the help of this battery. So these two battery are used for biasing of the transistor in case of the NPN transistor, and similarly these two battery are used as a biasing of the transistor for PNP transistor. So in this way the biasing are given and a signal is provided to the input to get a proper output. So in this way a common emitter configuration can be built up, and we'll see how this characteristics looks like for the common emitter configuration. So common emitter configuration, the base current amplification factor is called the beta for the common emitter configuration. In common emitter configuration, the input current is base current and the output current is the collector current. The ratio of the characteristics is collector current to the change in the base current is known as base current amplification factor, or beta. Beta can be derived as delta IC by delta IB. Normally only 5% of emitter current flows to the base, so the amplification factor is greater than 20. Usually the range of the beta is starting from 20 to up to 500. So each transistor, there is each beta, there will be no such transistor in the world having a same beta. So beta is the amplification factor. It is the ratio of the output current to the input current. Here we can see the output current is the collector current in case of the common emitter configuration, and the input current is the base current for the common emitter configuration of this transistor. So it is the ratio of the output current to the base current. So delta IC by delta IB is called the gain of the common base amplification factor of the common emitter configuration transistor. So in this way we can derive the beta, which is delta IC by delta IB, and we can represent it mathematically with the help of this expression. And we have to keep in mind the range of the beta is between 20 to 500. For different transistor there will be a unique value of beta which can get from the transistor. So now we are going to establish a relationship between the beta and alpha. We have discussed the alpha. Alpha is the IC by IE, and where beta is the IC by IB. So from these two equations we will discuss, and it is the transistor equation IE equal to IB plus IC. With the help of these three we will establish a relationship between alpha and the beta. So we just differentiate delta IE by equal to delta IB plus delta IC. So IB equal to IE minus IC. So we just put the value of beta equal to delta IC by IB. So in this way, if we simplify this equation, so beta equal to IC by IE plus IC. So you just put the value of this and we can get the expression in terms of alpha like this: beta equal to alpha by 1 plus alpha, 1 minus alpha, sorry, and the beta is, so this is the final expression of the beta in terms of alpha, beta equal to alpha by 1 plus alpha. So in this way our relation established between the alpha and beta, and we can compute the alpha and beta value in this way. So expression for collector current. So we have to find out the collector current. The collector current equal to IC equal to alpha IE plus ICB, which is the reverse collector current flowing from the collector to base, as the collector base junction is in reverse bias. So there is a leakage current flow between the collector to base, and which is mathematically represented as ICBO. It is the reverse leakage current of the collector junction. And IE equal to IB plus IC. So we put the value of IC in this equation and we get the value like IB equal IB plus alpha IE plus ICBO. Now you just get the value like this: I taking IE common, alpha plus 1 minus alpha equal to IB plus ICBO. In this way we get IE, and similarly IC. So in this way we can find the collector current. Now we are going to discuss about the characteristics of the common emitter configuration. In this common emitter configuration, the emitter is common, and it is the input characteristics of the common emitter configuration. So VBE, that means base to emitter voltage, versus IB characteristics is called the input characteristics. IB is increase rapidly with VBE, that means base to emitter voltage. It means the input resistance is very small, i.e. almost independent of VCE. IB is of the range of microampere. That means in these input characteristics we can see a curve like a forward bias characteristics of the diode. In case of common emitter configuration, the base to emitter junction is in forward bias, and we can get a input characteristics curve like a forward bias characteristics of a diode. So in this way we can characterize the input characteristics of a common emitter configuration. So now we come to discuss about the output characteristics of the common emitter configuration. In case of output characteristics, we can plot the graph between the VCE versus IC, that means emitter to collector voltage versus collector current. Characteristics is called the output characteristics. The IC varies linearly with VCE only when VCE is very small. As VCE increase, IC become constant. So in this way we can plot the graph of a output characteristics, and IB, that means the base current, as an parameter. We can plot this graph between IC in y-axis and VCE in x-axis with different IB. These are the different IB. We can get different plots of graph in the output characteristics. So it is the plot of the graph of output characteristics for a common emitter configuration. Now we are going to discuss about the input and output resistance of a common emitter configuration. The input resistance is the ratio of the change in the emitter base voltage to the change in the base current is called the input resistance. That means the resistance is voltage by current, R equal to V by I. So here we are going to determine the input resistance. So input resistance is the input voltage, which is VBE for the common emitter configuration, and IB is the input current for the common emitter configuration. So in this way we can derive the input resistance of a common emitter configuration. Now we are going to discuss about the output resistance. The ratio of change in collector to emitter voltage to the change in collector current is called the output resistance. So the output resistance is the output voltage, which is VCE, the collector to emitter voltage, and the IC is the collector current. So in this way we can plot the output resistance, or can derive the output resistance in terms of output voltage, which is delta VCE, and the output current, which is delta IC. So in this way we can mathematically represent the input and output resistance for a common emitter configuration. Now we are going to discuss about the common collector configuration. The common collector terminology is derived from the fact that the collector is common to both the input and the output side of the configuration. So in case of the common collector configuration, the collector terminal is common for both the PNP and NPN transistor. It is the NPN transistor and here it is the PNP transistor. So in case of the both of the transistor, the collector terminal is common to the both input and output. So, and another thing, the emitter based junction should be in forward bias and the collector based junction should be in reverse bias to get a proper transistor action. So in this way the common collector configuration can be made. In case of common collector configuration, let us find out the amplification factor, which is denoted as gamma. In common emitter configuration, the input characteristics is base current and the output characteristics is emitter current. The ratio of change in emitter current to the change in the base current is known as current amplification factor in common collector configuration. So we can find the common collector configuration as amplification factor by gamma equal to delta IE by IB. That means the output current divided by the input current. This circuit provides the same gain as CE configuration, that means common emitter configuration. So the delta IC is almost equal to delta IE. Now we are going to make a relationship between the gamma and alpha. Gamma equal to delta IE by IB and alpha equal to delta IC by IE, and it is the transistor current equation, IE equal to IB plus IC. So delta IE equal to delta IB plus IC. If I take this IB this side, so IB equal to delta IE minus IC. Now we just put this value of IB to this gamma value and we can get gamma equal to delta IE divided by delta IE minus delta IC. Now we put the values in case of gamma and we just divide the whole equation divided by IE, delta IE. So delta IE by delta IE, so delta IE by delta IE minus delta IC by delta IE. So delta IC by IE gives me the alpha. So the whole expression comes to 1 divided by 1 minus alpha. So in this way we can get a relationship between the gamma and alpha. So the gamma equal to 1 divided by 1 plus alpha. So it is the mathematical representation between the gamma and the alpha. Now we are going to expression for the collector current. So the collector current equal to alpha IE plus ICBO. ICBO is the reverse leakage current through the collector junction and we just, it is the transistor current equation, IE equal to IB plus IC. IB equal to, we just put the value of IC and we make a simplification of these equations and we get a collector current expression, and here we can see the relation between the alpha and beta. Beta equal to alpha by 1 minus alpha. There are various form of alpha and beta. Relationship between the alpha and beta, all are same. Now we are going to make a comparison between the common emitter, common base and common collector configuration with respect to different characteristics. We are going to differentiate between this with respect to input characteristics first. Input characteristics or the input resistance. In case of common base, the input resistance is very low, in order of 100 ohm. In case of common emitter configuration, the input resistance in order of 750 ohm, which is also very low. In case of the common collector configuration, the input resistance is quite high, in order of 750 kilo ohm. In case of common base configuration, the output resistance is very high, in order of 450 kilo ohm. In case of common emitter configuration, the output resistance is also pretty much high, in order of 45 kilo ohm. In case of common collector configuration, the output resistance is low, in the order of 50 ohm, which is very low. In case of common base configuration, the voltage gain is about 150. In case of common emitter configuration, the voltage gain is almost 500, and in case of common collector configuration, the voltage gain is very less, it is less than 1. The common base configuration, it is the application for high frequency application. The common base configuration can be used. In case of common emitter configuration, it can be applied for the audio frequency amplification, and in case of the common collector configuration, it can be applied for independence machine. Impedance matching, sorry, it is the impedance matching. That means when the two input and output resistance are not equal, or there is a mismatch, then it is used for impedance matching. Common base configuration, the current gain, there will be no current gain. In case of common emitter configuration, there is a huge current gain, high current gain, and in case of common collector configuration, the current gain is appreciable. So in this way we can differentiate between the common base, common emitter and common collector configuration of BJT. So that's for today. Thank you.
Thank you for watching. If you have any queries, you can contact to me. The contact number is given. The same number can be used as WhatsApp number. If you have any queries or doubt, you can call me or WhatsApp me to this number. Thank you very much.